In this part of the lecture, we will talk about some architectural trends that we are seeing and why they have led to the advent of multi-core processors. We will next go over to what is a parallel computer system anyway, some examples of real parallel computer systems, and a very brief introduction to parallel programming. But let's first start with the architectural trends and why multi-core. This graph shows what I call the free lunch that we had between 95 and 2000 about. It shows for the years of 1995 to 2000 how the performance in terms of spec CPU integer benchmark numbers, how they were improved from 95 to 2000. And note that the y-axis scale is a log scale, so the straight line here, or approximately straight line here, shows that there is an exponential increase in performance during these years. And more or less without doing too much of effort from the programmer. It's all sequential, and clock speeds increasing and architectural increasing and other things increasing led to this enormous improvement in performance. Look at the same graph for a little bit different benchmark suite, but nevertheless a spec CPU benchmark suite ranging from 99 to 2006. The curve is not at all linear any longer, which means that we have left the exponential increase in performance. We still have some in performance, but it's very much flattening out here at the mid 2000s. So what has happened? Well, the free lunch performance gain tracked the more or less the same curve as the number of transistors on a chip, which also is called Moore's law. So Moore's law specifies that we double the number of transistors every 2 years, and again we have a log scale here, so that from one line here to the next one is a factor of 10. And the straight line here shows that we have an exponential increase in the number of transistors. And see, this is not at all leveling off here around after 2005. It's actually progressing more or less the same. However, the clock rate was quite different. So roughly 2004, the maximum clock rates in processors stopped increasing. So here we have the plateau of the clock rate. We're not increasing clock rates any longer. So this is part of the reason for why we can't increase performance, but there are other reasons also. So the hardware evolution is that there are some limits to automatic improvement of scalar performance. We have, on the one hand, we have the power wall. We can't increase clock frequency without exceeding air cooling. And the reason for that is partly because of this formula here. The power consumption of a CMOS chip is, or not equal, but sort of proportional to the clock frequency. This was wrong. The voltage square, and then an activity factor times some kind of capacitance. Important factor here are the clock frequency and the voltage, the main voltage level. Furthermore, we have the factor that the maximum clock frequency that we can have is proportional to the voltage also. So we can't go too. So obvious explanation here, or obvious solution, is to lower the voltage levels, because that would increase performance, but that will also lower the clock frequencies. Anyway, with the increasing clock frequency we had, which also meant that we can't really counter that with lowering the voltage levels, we have an increasing power consumption, and this led to sort of extreme sort of cooling equipment for the high frequency processors. Second factor here is the memory wall. Access to data is really a limiting factor. With higher performance processors, they want to get data from memory and they want to get instructions from memory at a higher rate than before. So, and doing that is really a challenge. Many levels of cache memories, but still many problems. All the modern processors, or the high performance processors, also were in parallel in the sense that they can utilize instruction level parallelism, or ILP. However, it's been excessively difficult to extract more instruction level parallelism out of programs. Basically, all the instruction ILP that were available in the programs were used, and the only way to get out more ILP of it would be to rethink the whole programming model totally, and nobody really wanted to do that. So the conclusion here is that automatic improvement of single-threaded performance had to stop, and the only way to require performance to get performance scaling is to have explicit parallel mechanism and explicit parallel programming. And this is more or less what this course is about. So if we look at hardware trends, looking at how many cores or even thread count you would see on a processor, you see that up until around here, beginning of 2000s, there were one core per processor, but about 2002, 2003, we began to see hardware threads here. This point is when the first hyperthread processor appeared on the market. And then about 2006 or 2005 and 6, we began to see dual core, then quad-core processors, then 6-core processors, and this is not the latest diagram here, but there are up to 12-core processors from Intel, and of course if you look at other vendors, you'll see many more. So we have increasing parallelism, in hardware, and then we can also look at how big are the registers that you have in the processor. Wider registers means that you can fit more data in a register, and with more data you can do more operations in parallel. So this is by using what's called the SIMD, or single instruction multiple data instructions in processors. We have such that we have SSC instructions, we have AVX, and this is from Intel, and other vendors have similar kinds of. And you'll see here that most from 1980 and onwards, or even from the 70s, this has been steadily increasing, and with a higher increasement rate at the later years. And now we have processors with 512 bits. This will fit 16 single precision floating point numbers in a single register, which means that you can do 16 wide operations with a single instruction on these elements. In 2012, looking back, the state of the art in high-end processors were that we have, for instance, the Intel Sandy Bridge, 6 cores, 130 watts. We have the Intel Ivy Bridge with 12 cores, 24 threads. So typically the Intel processors are dual hardware threaded. We have the AMD Opteron 6284 with 16 cores. We had the Oracle UltraSpark T5 with 16 cores, and UltraSpark, the Spark processors, really lead the trend with the number of hardware threads. But also on the embedded side, we have a lot of multi-core. For instance, the Freescale T4240, 12 cores, also this multiple hardware threads. NVIDIA Tegra 3, and there are now Tegra Force also, as well, which has 4 ARM cores plus a very low power, low performance core, and then some accelerator heterogeneous computing. We have the Tilera TileGX with up to 100 core processors, and we have the Adaptiva Epiphany, which is another kind of embedded processor with 64 cores. Look at the difference in power consumption. The processors of the high end had 130 watts, 115 watts, 140 watts. I couldn't get the number for the Spark. And here we have 35 watts, 1 to 2 watts, 50 watts, and 2 watts here again. So a really big difference in power consumption. So we're going many core. We're going from a few cores per chip to many cores per chip. So what does that mean for us? Well, software developers were used to ever-increasing performance for free, increasing clock frequencies, increasing advanced architectures, exploiting the ILP, larger cache memories. But because clock frequencies no longer go up, we exhausted the memory ILP in applications. So parallelism is the only way of increasing the performance significantly. Which means that software development equals development for multicore. There is no way around it. We have to deal with multicore processors. So some software engineering considerations here. One problem is that the serial fraction of your program limits your performance. There's something called Amdahl's law, which I will be telling about later on, but let's look what Amdahl's law says. If we sort of illustrate the execution of a program as having a serial part and having a parallel part, if you can sort of divide all the parallel part in one end and the serial part in one end, then if you go parallel, sort of the only way to improve performance then is you can't really do much about the serial part. It's still serial, but the parallel could possibly be improved. So here's the serial part. In here we have running on one processor, and here we have on n processors, and this is then part of the parallel code divided by n processors with ideal speed up. So if you would plot how much faster a parallel program went, or which is also called the speed up, if you plot that to the number of processors, you will see that it can go sort of quite well in the beginning, but eventually you'll taper off the performance, and because the serial part becomes dominant then. So the scaling of a parallel program is limited by the serial fraction of the program. The solution here is to scale the parallel part of a program faster. So if you add more data to it, using data parallelism will hopefully reduce the execution time more faster of the parallel part than the execution time of the sequential part is increased. Second problem here, scaling can be severely strangled by a lot of locking, access to data, memory and communication, and many overheads. In fact, the speed up is actually does not really look like this. It's more likely that it looks like this. And it goes down again with more processors because we have a lot of locks and we have a lot of access to data that becomes contended, and many kind of overheads that increase with increased number of processors. Solution here is to use programming approaches with good data locality, low overheads, and avoiding locks. Finally, parallelism introduces a lot of new debugging challenges. We have deadlocks and race conditions and so on. And the solution here is similar to the second problem here. Use structured programming strategies to avoid these by design and also improve maintainability. And that ends this module, and now it's time for a quiz.